My name is Tom Herbert. I'm going to talk about Identifier Locator Addressing. This time around, it's going to be more about the implementation, so hopefully some of you are at least familiar with this. It's been a proposal we've had going on, I guess, 3 or 4 years now. Started at Facebook, and then kind of grew into some IETF. Not started at Google, I can't remember now. Anyway, next slide, please. Oh, I do the slides. I thought it was voice recognition, so sorry. Okay, so ILA in a nutshell, it's a mobility type of protocol, and this is using a type of address transformation where we split IPv6 addresses into a locator and identifier. So locator is kind of like the where of the packet, and identifier is the who. So the analogy I usually use is somebody has both an address where they might live, but they also have a name. So if I want to send a packet to somebody, I give the address and the name on the mailing envelope. And if that person happens to go to a different house or get in their car, their name does not change, so that's their identity. So that remains with them, but their location does. And in order to send to them, I have to now update their location, but their identity remains the same. Hopefully I can find that. So the analogy is pretty strong, keep it in mind, because as we go through with this, we'll see that the kind of the address lookup for names has a lot of parallels to that. So some important things, applications, they only see identifiers in this sort of protocol. Locator is the current location, and as we mentioned, that can change. The lookup that I just mentioned is a sort of database that maps identifiers to locators. It's usually like a lookup table. So Tom is at this address, so we kind of match those two pieces of information. ILA nodes do address transformation, so this gets a little more into the details of the protocol, and I have a slide that'll show that a little bit in a little bit. And one important thing about ILA, it is not NAT. It's address transformation. And this came up on one of the mailing lists a little while ago. The fundamental difference is that there's no loss of information during an ILA transformation. So going back to the analogy, if I send a letter through the post office, and they might rewrite the addressing to be, or my name or something like that to be some other location, and use that for forwarding the packet. They might put in another envelope, for instance, to send it to the local post office. At that local post office, all that information is removed, and we get back to this was the original packet or letter. So important thing, ILA, not NAT. So this pictorially is the addressing and transformation of ILA. So you can imagine at the top we have an IPv6 address. It's split down the middle in a canonical fashion. So the top 64 bits are what we call a SIR prefix, standard interface representation or identifier representation. And the bottom is the identifier. So the identifier is that component that is constant within the network or within the domain. So every host, every VM, every individually addressable node, for instance, would have a unique identifier. It's in 64-bit space, so that's pretty reasonable. The SIR prefix is really the routing component of this. The SIR prefix, to start with, is very generic. For instance, all of the nodes in a particular network could share the same SIR prefix. That actually might just be the routable prefix for, say, a provider that's running ILA within their network. So it could even be globally routable. The transformation occurs when we rearrange that SIR prefix, and actually the second line should actually say locator. So the SIR prefix is written into something called a locator, and this is routable within the network, and this is the part where we use this to get packets to where they're going. The analog to an encapsulation is when we do an encapsulation, say a VXLAN encapsulation or IP and IP, we put an extra IP header on the outside of a packet, and that destination address is now really the locator. So ILA is very simple, kind of almost a simple form of encapsulation or compressed encapsulation from that point of view. So this transformation to a locator is done in order for the packet to transit the network. And at the peer, like I said, at some peer endpoint, there's a reverse transformation to get back to the original packet. So this is a little more topological as to what the packet is doing. So you can imagine the source, some application running, they get a SIR address. A SIR address is the common prefix plus the identifier. So in this case, the prefix might be the quad 3, the : : 1 is the identifier. So applications see this, they're very visible. They don't convey specific location information. They can be in DNS, very public. So the source sends a packet, and somewhere in the path, we have to deduce where is this identifier, which is indicated by the : 1, where is that node actually located? So it's going to be somewhere, but that could be a mobile destination. So in the beginning, this might go to something called an ILA router, which does the lookup on the IP address, or at least the identifier. That maps it to a locator. The locator is that routable prefix that actually gets to the destination where the node is currently at. So in this case, the locator is quad 2 : 1. That's just basically saying there's a 64-bit prefix that's assigned to some intermediate node, possibly even the end host, but some node that is the location of this particular identifier. So the transformation happens in line with, first we do the lookup, then we do the transformation. There's an override of 64 bits in the top bits of the destination address. Then the packet's just sent back into the network, and now it has an actual routable locator to it, so the packet gets routed to the destination where the node is currently at. And at that point, when it's received, we have to undo this process. We have to get back to the original packet. So we just simply reverse transform the quad 2 : 1 : 1 back to quad 3 : 1. And so the application at the end, its destination address that it sees on its packets is again the quad 3 : 1. So this is pretty simple concept. One thing that would be nice is to eliminate the triangular routing here. So do we always want to have to go through this ILA router? So in order to do that, we do have a concept of redirects. This is very similar to an ICMP redirect. And the idea is if the router gets a packet, it might want to send back redirect information towards the source at least, saying there's a better path, you can do the ILA transformation yourself. So that's what number 3 would do. And that goes back to the source. And then after that, like in point 5, the source host can actually send directly. So this is actually kind of a 2-level routing hierarchy. So the ILA routers, you can imagine those are actually fairly high-load routers in the network. And maybe the devices towards the source or at the source are more caches for ILA, and they just have a working set. And as long as they're within that working set, we can avoid the triangular routing and get a very direct path. This is going to have a lot to do with how we want to achieve low latency or super low latency in networks by getting down to the most direct path in mobile, so that instead of going 5 hops deep into the network, we can only go maybe 2 or 3. So there's going to be a lot of latency savings there. A few benefits of ILA. It's no protocol overhead. So like I said, encapsulation is not involved. No extension headers are required. That has a few ramifications. So one of the big things is there's no typical tunneling issues. Anytime we do tunneling within the network, we have to consider what happens if, when we increase the size of the packet, it exceeds MTU. So that is a little bit of a pain to deal with. It's multiple use case. So we started this as a way to do data center virtualization. It's kind of morphed into also a mobility solution for mobile networks. In the mobile networks, this would be a mechanism to provide anchorless mobility, particularly the redirect mechanism may help there. We're also advocating strong privacy and addressing. This has a lot to do with the exposure of kind of personally identifiable information in addresses. So you can imagine if I have a mobile network and my eNode Bs, which are basically the end devices at cell towers, those have a very specific location. And if my locator is exactly the address of one of these eNode B end systems, if somebody sees that, they see they're sending to their friend, or maybe not even their friend, ex-girlfriend or something like that. They're sending to them. We don't want them to be able to look at the actual addresses and figure out where they are with any specificity. So we want to keep that kind of hidden. So ILA does have those components. There's also some more general, how do we do privacy and addressing that we're looking at. Flexible and scalable control plane resistance to denial of service. This is kind of interesting, especially with the redirect mechanism. There are some properties that make this more appealing than, say, a more like an ARP type of mechanism where you request the next hop in the ILA and you get a response. So the reason we don't like that is because a lot of this could be user-driven in, say, a mobile network, where we don't want every time the user creates a new destination, we're doing this long lookup, installing packets and things like that. So denial of service is a really critical component of this, especially in the control plane. And then we have an upstream kernel data path. There's also some other work. VPP has something. And we also have an XDP implementation. But today we'll look at the kernel side only. So speaking of the kernel, so ILA has been in upstream Linux since about 4.3. The modern version came in at 4.15. This was actually changing how we do some of the checksums and how we integrate types into the ILA kind of address structure. It's a kernel module. It's ILA, loads pretty easily. One of the big wins was lightweight tunnels. Once we have that, that allows us to integrate the ILA processing, the ILA lookup into the routing table. So on a host, this is especially important because then we can cache the route lookup in TCP connection. So ILA can be done without any sort of lookups on the transmit path. Then receive path, we hooked into the pre-routing hook. We needed something before major packet processing, early demux happened, so we used that as a routing hook. Pretty lightweight. That's where we do the reverse transformation after packets received with an ILA destination. And then, as I mentioned, we have ILA and VPP and XDP. So in terms of performance, this is the latest performance numbers I ran. It's kind of a grand view of all the major encapsulations and includes segment routing in IPv6. And these basically divide up into some major categories. So all of the IP and IP encapsulations, especially the UDP ones, are pretty much the same latency, same performance. Kind of makes sense. So once we get the checksum squared away, get the hash for UCMP and RSS squared away, it works out pretty well. IP and IP is kind of interesting. So not a UDP encapsulation. This one can go either way. So one thing I should mention is a lot of the performance difference here is dependent on the hardware accelerations, in particular checksum offload and RSS. So this was done on a, I think an Intel. I'd have to check it, but whatever it is, it supported IPv6 and IPv6 encapsulation because we got, actually didn't support it for RSS, but it might have supported for checksum. So we got kind of a lower TPS, but if you look at the encapsulations, because they have RSS for UDP, we actually got much higher throughput. Pretty typical what we see. Either RSS works or it doesn't in this sort of test. So segment routing was kind of interesting and kind of had mixed results. So the segment routing inline, which is where in order to do RSS over the ports or checksum offload, you would actually need the device to parse over the segment routing headers. But segment routing encap apparently worked fine, so that was kind of, or I guess it's vice versa. So one of them works, one of them didn't. But ILA, the thing I wanted to point out here, it actually is the closest of any overlay technique or encapsulation technique that I was able to test. So it's about 3% within native IPv6. So that's almost purely just the processing overhead. In this test, there was one lookup, simple hash lookup, and then the overhead to manipulate the packet. So it's probably pretty close to as fast as we're going to get for an overlay technique. So ILA control plane, this is the part where we manage the mapping tables, and this is a whole topic in itself. It's definitely, and in some sense, it's an elaborate it's elaborate router daemon. Our decision there was to actually use a database to do the backend information. So this is kind of in lieu of using a routing protocol. So we are seeing kind of this trend towards routing systems. I think Facebook actually has a great example where an actual database is used to synchronize the information, do convergence, and things like that. So right now we're using Redis. This could turn into a distributed hash table or other possibilities. But the important characteristic here is this is a fixed length lookup, so it's a simple key value lookup. Database is great for that. Key value stores are great for that. And we actually divide this up into 3 databases, so I'll kind of have a little more information on that. But there's a locator database, identifier, mapping. So in the GitHub, you can also find a number of executables to control this. So there's some control daemons, and also a CLI that allows inspection of the databases, inspection of the mapping table, and kind of to control the mobility. So the architecture of the user components, there's 3 major types of nodes in ILA. ILA routers, I already mentioned, those are kind of the central points. Once a packet's routed to an ILA router, it's expected to be able to convert the server address to an ILA address, or the route doesn't exist. So they are kind of authoritative from that point of view, kind of like a router, a normal router in that sense. We do know that there's potentially a lot of mapping. So every node, for instance, potentially has its own mapping. So scalability comes up very quickly in these sort of mapping systems. So these effectively become host routes. So you could have millions and millions of these. So scalability on something like an ILA router is going to be important. And that quickly gets us into, we need to shard the mapping space in order to have multiple routers, and each of them takes care of part of the space. And then in a real deployment, you'd obviously want to replicate each of those routers to some extent. An ILA node, on the other hand, is more of the endpoint in the network towards the user. It does 2 things. One is it handles the ILA to server address translation. So when packets are coming into an end device, for instance, with an ILA address, this is a location that actually transforms the packet in preparation to give it to the application. So it's kind of the terminal point for ILA. There is something called an ILA host, which is the same thing, but it's actually host-side functionality. The only difference there is an ILA host actually has some opportunities to integrate with some other parts of the stack, like I mentioned, the TCP and the early demux. So the ILAM is the management plane. That's where the databases are housed and where we have a control daemon. So all of the management goes through this, and the ILAM basically programs the ILA routers with some sort of protocol, and they may actually, routers themselves might actually talk with the ILAN over a caching protocol. And then the pink line is kind of a simple data path. Reference topology, so I won't say too much about this. It kind of is a similar description of what I just described. Say the ILA routers, all the edges, those would be kind of the analog of border routers, probably the same location. And ILANs would be in the network. These would be where caches are housed closer to the user. And then your ILA hosts may be mobile edge computing or hosts like that, where we're interested in optimizing the application. So it makes sense to put ILA in conjunction with the actual host. So given that, I do have a demo. And this is the kind of the demo topology. It's basically a mobile network in a box. So the way this is structured, it's going to use network namespaces in Linux. So the things in parentheses are all the different namespaces. And this is kind of a construction to emulate a mobile network. So the RAN simulates the backbone. We have an internet host out there. It talks through a gateway into the radio network. And then there's some number of eNode Bs. Again, those are kind of the base stations. So we have 10 of those. And below that, each of those has 10 end hosts, user equipment in mobile terminology. So the databases, the locator and the identifier, these describe the components. What what identifiers are in the system, what locators are in the system. The initial mapping is in the identifier locator database to, or identifier database to locator database. And then the mapping database is more the operational one. In this case, we don't have a control plane yet, or a specific control plane protocol. Everything's done through a shared database. So before I go to the demo, let me talk a little bit about the futures. So one of the things we want to have is something called ILAMP, ILA mapping protocol. This is a cache management protocol. So if you remember, the ILANs might have a cache. This would be something that handles the ILA redirects, for instance. So we do have a protocol for that. My personal preference is that we just move this all to TCP and REST, and then have a nice, simple, yet extensible protocol to say, here's the identifier, here's the map, go ahead and use this from now on. So it shouldn't be too complex, but given the way these sort of things work, I'm sure there'll be extensions and what have you. And so the other thing is, there's an alternative approach. So in a normal type of mapping system, you have a lookup that happens on every packet. Say when a packet hits an ILA router, there's a lookup. As I mentioned, this can be very expensive. There could be completely different alternatives where we actually somehow carry the locator information in the data packets themselves. And the idea is we tell the end application, we give it some token, we actually call it tickets in our proposal. Excuse me. We give the end host a ticket and say, put this onto an extension header. We understand what it is, you probably don't, but this somehow encodes the locator information. So when the packet is sent, say from a UE, goes into the network, if it's sending to the internet, there's actually no need for ILA because the destination is on the internet, so the packet's just routed normally. The interesting case is usually coming back. So when packets enter a network, a mobile network, we have to find the destination for them. So that's where we do the lookup normally. But in this case, if we have the information attached on the outgoing, and somehow the server is smart enough to reflect that information on reply packets, then those reply packets that come in, they have this information attached, and this router at the border can actually look at that and say, oh, the locator is embedded in here, I can just use that information and send directly. So we don't need the lookup, and conceptually this may be able to scale the number of nodes. Scaling is going to be a big issue here for various reasons. Even today, we need about 1 billion nodes, but that could go much higher with some of our addressing models. So there's probably some other things with that, but I would like to do the demo. So we'll see how this one goes. So all of this is available in GitHub, and what we're going to do first is create that topology. So what it's doing, it's creating the network namespaces. The first few things, we're creating the Redis databases. So as I mentioned, there are 3. And those primarily run in the RAN namespace. Then we created the 10 enode Bs. And then we created the, let's see, we're in the UEs. So we're creating the 100 UEs. And then after this, we'll attach them. Obviously, this is pretty slow. So I think it has a lot to do with the scripting and kind of this. The interface model is pretty crazy, so we're having a lot of network interfaces. I think moving forward, when we get a little closer to full-scale ILA deployment, we're obviously going to need a better emulator of this, be able to create networks much larger automatically and emulate them. So it's almost done with the first 100 UEs, and let me prepare the next step. So as I mentioned, code is on GitHub. One of the things we try to do is make it really easy to build. So one thing I noticed doing user space development, kernel as complex as it is actually has a pretty simple build environment. once you get into some user space stuff, it's pretty crazy on the number of modules, packages you need to actually build something reasonable. Okay, so first thing, let's check out the network namespaces. So a whole bunch of network namespaces. So they're labeled UE, eNode B. There's a RAN 1, Gateway 1. If we look at the interfaces for one of these eNode Bs, basically every interface or every UE became a virtual interface. So one eNode B has 10 southbound network interfaces, then one northbound that goes into the upper layer, which in this case is the RAN. So all that seems to be set up. And we can look at the various tables that were constructed. So this is the locator list that I mentioned. The first number is just the index, so every locator has a simple index. And then the next number is actually the 64-bit real locator. So locator number 2 simply has 2017:00:2. So that's pretty arbitrary, but this is the part that's going to be routable on the network. So effectively, this is the address of an ILA node. So we can do the same thing for the identifier table. So this is a list of all the identifiers. So it has similar format. So the first number is just an index, so we can reference whatever identifier we want by an index. The next number is the SIR address for that. So the first part is the quad 3 again is the SIR prefix. That's our prefix. And then the number after that is just the identifier, and it's just simple increment and counter. So those are the first two databases, and as I mentioned, those are mostly used in the control plane. The one that actually kind of drives the instantiation of the mappings in the kernel is the mapping database. So this has a little more information, some information that could be used by the kernel. So if you look at the routes, so the routes at the top are actually the ILA LWT routes. These are fully instantiated. So the first thing is just a simple destination. So these become host routes on this system. And then the ILA LWT specific information follows that. So there's a few, there are a few options here. So one of the most important ones is checksum. So when we do the ILA transformation, we do want to maintain TCP and UDP checksum. So there's actually a nice trick that was created by some of the IPv6 to IPv4 network transformation. It's possible to actually maintain the checksum, which might have this, include the pseudo header in, say, TCP or UDP checksum, maintain that checksum to be correct even in flight. So we're changing the destination address. Normally that would affect the checksum and make it incorrect. But it turns out if you make an equivalent change somewhere in the packet to offset the change you just made, then it's kind of a checksum neutral thing. So pretty good discussion on that on some of the original work for IPv6 translation. So I just adopted some of that. The other things, there are a concept of different typed addresses. So we can support multicast, for instance. There's an IPv4 over IPv6 format. And this one is the canonical 64-64 split. Those are kind of optional, so per site you may or may not use something like that. So now let's try to crank up some traffic. So by the way, most of these commands, the first argument is running in the network namespace, so that's the argument that follows the command. So for instance, here we're running okay. So here we're running TCP dump on any node B, and then it's dumping that northbound interface. So if we ping, let's see. So here we are pinging. And if we look at TCP dump, the thing to notice is the destination addresses. So we're pinging quad 358, but you'll notice the address on the wire is, let's see, so the ICMP request is quad, or 2017:009. So that's the locator of quad 3:58. And then the identifier portion is this crazy 131C, is it? That's actually a result of the checksum neutral. So the checksum neutral fits in there. That's actually the correct value for identifier 1. So the remote peer knows to, when it does reverse transformation, to undo the checksum neutral, and it will wind up at the original destination. So you also notice that the replies also are doing ILA. So we're coming into this address, and they have a similar transformation. So ILA can definitely be applied in both directions. However, you also notice the source address does not do ILA. So we never actually do ILA in the source address. It's only destination. So now, let's get TCP dump. So basically, we have one UE pinging to another. And let's see what happens when the UE we're pinging goes off the network. So the sun attached it. So meaning now this UE went out of range. It's not really attached to anyone, so it's out of it. So what happens? Ping stops as it should. And system still knows about it, but doesn't have any location, so any packets just are dropped because there's no route to it. So sometime later, maybe this is a car, and it comes back in the network, but now it comes to a completely different cell site. So we can reattach that node, node number 88. Now instead of being on, I think it was 8 before, now it's on eNode B3, so it went from one to the other. So that process actually is very specific in the mobile world. It's called Handover. If you remember the discussion we had yesterday on super low latency, it's one thing to have super low latency in the data path, which I think something like ILA would provide. But you also have to consider this case where I have an application running, and just by virtue of passing from one cell site to another, I really can't afford to take a several hundred millisecond hit. So the latency for this actually becomes very imperative, and it is a difficult problem because it has a lot to do with how to get the control plane, the actual radio networks, and all of those to cooperate. There's some interesting solutions. Some people actually, when you know you're going to transform or move to somebody else, they actually fork packets and like replicate them. So there's some interesting possibilities there. In any case, I think that's all I had. Are there any questions?
So what's the difference between this and Lisp?
Excuse me?
So what's the difference between what you're proposing here and Lisp?
And Lisp?
You've never heard of, have you heard of Lisp?
Lisp, yeah, sure. Lisp is an encapsulation, and for this purpose, we can divide the world into two types of things. So one is more address transformation. You could almost argue that NAT actually has some of these similar properties. And Lisp is an encapsulation. The primary difference here is simply we're not adding anything to the packet. So a packet sent from an application, say a TCP packet, the address is transformed. On the network, it's still TCP, which does have a big advantage because networks have been built out to support TCP, UDP. They're already aware of that. It also has the advantage we're not making packet headers bigger. If you look at the IoT space, for instance, packets are actually getting smaller. So a packet from a sensor may have 100 bytes. If we're adding another 200 bytes on that, or 300 bytes, like some of these more rich functionalities could have, so Lisp or segment routing, you end up having a lot of packet overhead for a little data. So you would think in the modern world this isn't an issue, but there are still bandwidth constrained links We know from LOPAN and things like that where this is actually compelling. So in some sense, it accomplishes some similar goals. It is identifier locator, but the mechanisms and in particular the packet format are pretty different. The control plane actually could be leveraged, and we are talking with the Lisp guys and some others. Could there be a common control plane to control this?
Any more questions?
All right, I'll take that as a no. Thank you.
Thanks, Tom.